In this video, I'm going to be comparing Valve's new Steam controller against a regular keyboard and mouse in a 3D modeling program known as onshape. This comparison is going to consist of 5 parts, starting with fixing the constraints in 3 different sketches. Then I'll create a 2-inch cube followed by 1x2 tube that is 20 inches long. After I complete those challenges, I'll create and assemble a simple FRC drivetrain consisting of 4 tubes, 4 swerve modules, and a belly pan. And to wrap things up, I'm going to design a simple electronic mounting plate. Getting started here with the Steam controller, you can see that I have a timer set up on the right side, and this first constraint challenge is making a square out of the given lines. So you can see me going with the Steam controller using the right trackpad as a mouse and using the left trackpad as a scroll wheel, and then using the trigger buttons as my left and right click. Going through this, both challenges are going to be the same for keyboard and mouse. So both will have the same challenges. The one downside to having the Steam controller is that you can't actually type normally. I did try getting the virtual keyboard set up, but I couldn't figure it out, and I was on a little bit of a time crunch, so I just decided to take it and use the keyboard for typing numbers and similar. The second challenge is essentially creating a small gearbox. I have all the gear sizes already set, but making them tangent to each other and all that. For example, we have our starter gear, then we have a smaller gear concentric to it, and we have the larger gear tangent to that with a smaller gear concentric to the larger gear. And then it's just locking that in place. And then here we go, moving on to the third constraint. Now, this one's a bit more difficult. It's not really going to be anything you see in FRC, but it's just a X pattern of 5 1-inch squares, all making them out of the lines. As we continue, we can see how I'm using the Steam controller in different ways, moving around the screen and such. Honestly, my experience with the Steam controller was rather nice, and I have to say Valve really did a good job with it. And as we continue, you can see that I end up finding a little issue that I had, which is something you can sometimes come up with, is where onshape decides constraints that you don't want. For example, that horizontal was messing up the sketch. You can see there that using the Steam controller and only having to press backspace on the keyboard, I was able to get that sorted out and continue along with my progress. Skipping ahead a little bit, I am almost completed with the third constraint challenge. You can see that I'm just finishing up connecting all the sides of the squares. The center square is completed, and I'm just connecting the squares together. And then I'm going to start making their sides all equal to that 1-inch square in the center, so that all of it is the same. A little bit farther in, I'm just finishing up setting all those sides to equal, and then it's time to move on to the next challenge, which is creating a cube from scratch. So to start this off, I'm going to be creating a new sketch on the top layer, and this is going to be a 2-inch cube. So 2 inches wide, 2 inches long, 2 inches tall. And you can see that I'm using a center point rectangle for this, and then having to use the keyboard and mouse to actually add the size dimensions in. But other than that, I created the square almost entirely with the Steam controller. Again, just having to use the keyboard for those numbers. And then you can see I just extruded it up 2 inches so that we have our cube. And then there you go, you can see it in 3D to show that that is in fact a cube. Moving on to our next challenge, which is a tube. This is going to be a simple 1-inch wide by 2-inch tall by 20-inch long rectangle tube for FRC robots. This is usually used in drivetrains and similar, or for other structural things. And for this tube, you'll see in a second that I'm going to be using a feature script known as Tube Converter, which is a really helpful feature script for converting 3D objects into tubes, such as this. So you can see it's blocked. The actual menu is blocked by the timer and camera, but you can see there that feature script allowed me to convert it to a tube and add all the holes I needed for it. Moving on to the drivetrain now. This is going to be the longest section of this for the Steam controller. This is going to be a complete FRC drivetrain. Well, not a complete one. A simple FRC drivetrain consisting of four 1x2 tubes as the mounting rails on the sides to give it structure, and then a belly pan on the bottom, and then importing West Coast Product swerve for the actual wheels and motors to allow it to drive. Starting off by creating a simple square in one side that is 5 inches by 5 inches. And after I create that square, I use a tool known as a circular pattern that allows me to create instances of that square in each corner without having to manually sketch them. And then I just go back and shift the blue squares so that I can constrain the center of that circle pattern to the origin of my sketch. And then now that that's done, I can go through and add all the sketches for the actual mounting rails on the drivetrain, which will be those 1x2 tubes. You can see as I finish that up, I am using the circular pattern again to create more instances of those without having to manually sketch all of them. And that also helps with dimensions because it copies all of them around. And then again, I just have to shift it so I can properly constrain the center of that circular pattern to the origin of the sketch. Then I'm going through and extruding each of those rectangles to 2 inches tall. And then I'm going to use tube converter again to actually turn all those into the tubes that are needed for a normal drivetrain. Now I am finishing up converting all those extrudes to tubes, and then I'm going to start working on what is known as a belly pan. The belly pan is a plate that's going to go on the bottom of the drivetrain, and that's going to allow the drivetrain to have more structure, along with add mounting points for various electronics and other stuff. So to create the belly pan, I'm using a tool called Gusset that allows me to select all the holes on the bottom of the tubes, and it'll automatically create a plate between them. So one feature of it that for some reason decided not to work for me is that you can actually select 2 holes and then select a third hole in between them, and it'll automatically do every hole for that spacing. Sadly, this time it didn't work, so I had to go through manually and select each hole. As you can see here, that's going very well with the Steam controller, and actually wasn't bad at all having to go through and select each hole. Skipping ahead a bit farther, you can see that I'm finishing up selecting all those holes using the Steam controller. And then now that is the belly pan of a robot temporarily done until I get the size for a swerve. And then here we are moving on to the assembly, where I'm going to import all the parts that I've made so far and then start assembling those into the drivetrain using mate connectors. So that's all being done again by the Steam controller, as you can see based on the camera. And it's just the process of going through and selecting the holes and their mates, and then selecting the holes on the belly pan so that they connect together and basically fix the tubes to the belly pan. As you can see here in a second, I am doing 7 holes in because I know for future reference, I'm going to have to cut sections out of each corner to fit the swerve. And it's easier to mount it with a hole farther in, so I don't have any issues with that hole being removed later and causing the mate to break. And you can see here that it is important that you are selecting the correct sides of your circles when creating mate connectors. For example, you could see for a second there that the tube was actually inside the belly pan, and that was because I'd accidentally selected the inside face of a circle, or the inside edge of a circle, instead of the outside edge. But you can see there that I got that all fixed, and that tube is now mounted in the right position. Skipping ahead a bit farther, I am almost done with mounting all the tubes for the belly pan. This is the final one that you can see I'm just finishing up right now. And then at first, I cut it out, but I was going to go to the West Coast Products website and get the onshape link for the server modules. But then I remembered I have FRC Design, which is a really helpful tool or add-on in onshape that allows you to import a lot of FRC components directly into your models without having to find their onshape links or download their step files and import them. For example, there you can see it has fasteners, bearings, pulleys, gears, electronics, all sorts of stuff. And I use that to import West Coast Products X2S swerve modules. I imported both left and right. And that is a really handy tool if you don't have it. I would definitely recommend getting it, because as you can see there, it allowed me to import the entire swerve module rather easily without having to go to West Coast Products website, find the swerve module, then open up the Onshape link, copy that link, then paste it into Onshape. So then you can see here that I'm going through and starting to mount the swerve modules into place. And that is when I realized my first big mistake. In the original sketch for the drivetrain, I had set the swerve square to be 5 inches, but I had misremembered and the actual size is 4, so I had to go back into the sketch and fix that, as you'll see that I'm doing right now. But that was a relatively easy fix, but that fix caused other issues, as you'll see later, with the gusset hole patterns and the tube mounting locations. But luckily that wasn't too much of an issue, and that got that all fixed. Then, as you can see here, I'm rushing to this next bit because this is just a bunch of mounting the swerve modules in their positions and fixing those tubes. As you can see there, I had the holes messed up, but I got those fixed in 2 minutes total, and then just remounting them there. Overall, that wasn't too much of an issue, but it's something to expect when you're designing, that if you change something, expect something else to change that you didn't expect. For example, those holes changed because the tube got longer, but I didn't think of that, and that messed up both the fasten mates for those tubes when I was connecting them to the drivetrain, and also messed up the actual hole pattern themselves. Just make sure to watch out for that stuff. And then that was the end of assembling the drivetrain. Now I just had to create the cutouts that go on the bottom of the drivetrain. Now, these cutouts basically gave clearance for the swerve modules, because you could see a couple seconds ago that the belly pan is actually inside the swerve, and that is because those cutouts aren't there yet. Once I add those cutouts, it'll have the proper clearance, so there isn't any interference between the belly pan and the actual bottom plate of the swerve. Now, to actually make those cutouts, I start by making a simple square that is the same size as the swerve modules themselves. As you can see there, though, it doesn't seem to line up, and I'm not sure why that happened. It is the same size lines. No clue why. You can see there that I spend a bit of time trying to get that fixed, but I end up realizing that they are the same size, even though it doesn't appear the same. So I just keep continuing as is, and then now that the square's done, I start making the actual cutouts for the swerve plates that actually mount the swerve to the tube, which were the 2 little ears sticking out in the bottom swerve plate back in that image I showed you earlier. And to make those is just a simple rectangle that is originally I made it inch wide. You'll see later I have to change the size of it. But it's a simple rectangular cutout, and then I just paste that directly between the 4th and 5th hole from the end of the tube, and you can see that I'm doing that there. I do have a little issue at the midpoint, so I end up undoing that, then going back and just using a regular constraint to move that into place. But that is just one cutout for one side, and then I use the mirror tool to actually replicate that rectangle to the other side, the cutout, so I don't have to manually sketch it. It's just selecting a mirror line and then selecting the parts that I want mirrored. And you can see there that that's all of them, then they're done. And then now that I have the sketches done, I do another circular pattern for all the pieces, and that will allow me to get the cutouts in all 4 corners without having to remake all of them. And then the same with the other circular patterns, I do have to go back in and shift one of them so that I can get access to the center point, so I can constrain that to the center of the origin. Now that I've finished up the sketches for the cutouts, I can actually go through and do a extrude set to remove. and actually just select all the edges of those sketches, and then that's going to remove sections out of the belly pan and actually create those cutouts that I need, as you can see that I'm doing here. And then after I finish up that last one and I confirm the extrude, you'll be able to actually see those cutouts there. And then now that those cutouts are done, you can't actually machine sharp corners very easily. So instead, when you ever have a plate that you're going to cut out on, say, a CNC, you need to round corners. So I start with a 4 mm radius for the outer corners, but later I do end up changing that to a 0.25-inch radius. And then for the inside radius, you always want it to be larger than the radius of your tool bit. For example, we use a 4 mm end mill diameter for most of our stuff. So when I go through and do the inner fillets, as you're going to see soon, you will see that I set it at a 2.1 mm radius, which is slightly larger than our tool. So it doesn't just stop and then immediately start another direction. It kind of does a little loop, a little like angle into it, so it's not as hard on the tool. Now that I got the fillets all finished up, I do a first check of the clearance. You can see there that I didn't size it correctly, so the 1 inch is basically right on, and you always want tolerance, so I'm gonna go through and change that. And then there are also a lot of clearances interfering with the actual plates themselves. And now you can see I'm going through and changing the actual sketches themselves, get more clearance. For example, there I eliminated most of the interference with the back plate, but then I just needed to go through and add a little more clearance. So as you see in a second, I now have a gap there. And that's going to make it so that when this drivetrain were to be assembled in real life, I don't have any clearance issues between the belly pan and swerve modules when it's trying to be assembled. And then that's the drivetrain all finished up using the steam controller, and I got that time locked in. So now it's time to work on the finalized mounting plate. I didn't really have a plan when I first went into this mounting plate, which is definitely a disadvantage of the steam controller. As you can see there, I just start by making a rectangle and then make a normal hole pattern for mounting to a tube. But as you'll see in a little bit, I end up scrapping that as I figure out what I actually want to mount. But as I said, that is a bit of a disadvantage to the Steam controller because I definitely spent a lot of time wasted just making that to then basically almost delete all of it. But I ended up picking a mount for a pneumatic control module, and using that as my reference, I then restart most of the mount. As you can see there, I deleted most of the lines. And then I start working on the new mount, which is going to be a simple triangle ISK mount where I have cutoff or angles, as you can see there, and then a flat face by the actual pneumatic control module. So this went actually very smoothly with the Steam controller until I got to these holes. I don't think it was the Steam controller's fault at all. It was something funny with onshape, where it didn't want to be, the holes didn't want to be concentric with the circles that I made. So I had to make them concentric, delete the mates or delete the connections, and then go through and add manual lines and dimension those to actually get their location. As you'll see later, it worked fine with keyboard and mouse, so I'm guessing it was just a temporary on-shape thing, like the lines not lining up when I was doing the cutouts for swerve. As you can see there, I get those holes all made, and then that's the main sketch for this mounting plate done. And then now I go to extrude it. I extrude it to 1/8 of an inch thick, and which is a bit thicker than what would be used. I guess it depends on where it's going to actually be in your robot, and where is it in a high impact zone, stuff like that. I just go with 8 for the familiarity, and then I do an offset so that it's actually modeled underneath the pneumatics. And then I start to go through and add the holes using Onshape's built-in hole tool. And that's going to be very easy with making, as you can see, they're selecting all the centers of the circles for the different holes. And that, once I select all of them, I can then select the starting face and the hole type, and then that is going to automatically all those holes, which is really nice, especially if you're doing drawings compared to just making those circles and extruding them as remove. Doing a hole pattern actually allows you to mark those holes as their correct size in a drawing. And then I do the same thing for the holes for the pneumatic control module. I start by just making them the same size, but later I do end up changing them to just a number 6 screw, which I found to be basically the same size for them. And then you can see here that I'm about to fix it because I accidentally pressed the wrong button. But there we go. I select a number 6 size, and then that's the correct hole size based on dimension. And then that just about wraps up our mounting plate. The final step for it is to smooth out the sharp corners using fillets. And I decide to go again with a 1/4 inch fillet because it looks good. It wasn't causing any issues from what I could see with the size, and that's basically it. I just go through, select each corner and all that. And as I finish up that final fillet, it is time to get our final scores for the Steam controller. The total time for the Steam controller was 39 minutes and 14.43 seconds. And I'll go more in depth into the timing for each of the individual challenges at the end of the video. Moving on to the keyboard and mouse, you can see that I've sped up the video a little bit so that we can actually get through this in a reasonable amount of time. But there we go, I just finished up the square for the constraint challenge with the mouse in under 40 seconds, and then I just got the circle set up. And then now I'm moving on to the X pattern of squares, which is taking a little bit longer, but still pretty quick on keyboard and mouse, as you can see by the sped up video. And then after I get those set up, it's time to move on to the cube, which I also get through pretty quickly with setting it up and then extruding it, taking less than 2.5 minutes for all 4 of those sections. Then moving on to the tube, I get started with the 1x2 rectangle and extrude that to 20 inches, and then use tube converter to turn that into a full tube with holes. And then it's moving on to the drivetrain. During the process of designing the drivetrain with keyboard and mouse, I go back and I reference the dimensions that I used for the Steam controller, and I made sure that even though they weren't the most efficient sketches, to do the sketches in the same way for keyboard and mouse to try and keep it a bit more fair. Then moving on, you can see that I am now onto the assembly portion of this challenge for the drivetrain, where I have all the tubes mounted, and then I'm just now adding all the swerve modules. And then after I get those modules set up, I'm going to go back and do the cutouts for the belly pan, as you can see that I'm doing here, just in the same order that I did as the Steam controller, with me making the first square and then doing the reference the sizing cutouts so it doesn't interfere, and then using circular pattern to do it on all 4 corners, extruding it, and then adding all the same sized fillets. And as I've finished up those fillets, I'm then going through and double checking sizing and then making sure I have all the swerve mounted correctly. As you can see, there are a few that were 1 hole off, so I fixed those, and then now it's time to move on to the electronics mounting plate. This one I had to heavily reference the Steam controller for a lot of the spacing on the upper angled sections, for both the size of the top line, how far away that was from origin, and similar stuff. As you can see though, it's going very well with referencing the Steam controller's designs and then going back to keyboard and mouse to continue designing. And then for some reason I did not have the same hole issue as I had with the Steam controller for making those concentric and then equaling them to the size of those holes. Not exactly sure why, but it was, I guess, something with onshape. Then you can see that I'm doing the same thing as well with offsetting the extrude for the mounting plate so that it wasn't designed inside of the actual piece itself. Now that I have completed all the challenges of both the Steam controller and keyboard and mouse, it's time to take a look at how their times compare. Starting with the Steam controller, we have a total time of 39 minutes and 14.43 seconds. It took me 40 seconds to fix the first constraint, 35 seconds to fix the second constraint, and 2 minutes and 14 seconds to complete the third constraint. Moving on to the cube and tube, it took me 49 seconds to create the cube and 49 seconds again to create the tube. The drivetrain took a total time of 23 minutes and 45 seconds to design, and the mounting plate took 10 minutes and 22 seconds to complete. Moving on to the mouse and keyboard, we have a total time of 18 minutes and 40.58 seconds. It took me 21 seconds to complete the first constraint, 25 seconds to complete the second constraint, and 1 minute and 12 seconds to complete the third constraint. Moving on to the cube, it took me just 19 seconds to complete it with the keyboard and mouse, but the tube took longer at 2 minutes and 42 seconds. But I believe that's because I accidentally forgot to mark the time when I actually finished the tube and accidentally did it later during the drivetrain when I realized I missed it. But moving on to the drivetrain, that took me just 9 minutes and 8 seconds to complete and finish, and the mounting plate took just 4 minutes and 33 seconds. Now, based purely off time, the Steam controller loses, but when you actually get into it, I feel like the Steam controller is definitely behind the keyboard and mouse, but not by much, because A, that was my first time ever designing anything with the Steam controller in a 3D modeling program, and 2, the keyboard and mouse had a major advantage going second because I found issues with sketches in the Steam controllers that took up more time that with the keyboard and mouse I already knew they were there, so I was just able to fix them quickly. And then also this shows just how useful and versatile the Steam controller is. And I think with practice, this is definitely going to be a good replacement for keyboard and mouse in tighter spaces, or if you have a laptop with a bad trackpad and you don't have room for a mouse, or if you just want to kick back, relax, get in a recliner and do some gaming on the couch, not gaming on the couch, designing on the couch with your PC connected to your TV. But all in all, I definitely plan on working with the Steam controller a bit more in Onshape for some personal projects, because, well, that was my first time using it, and it took over double the time to do the same stuff than a keyboard and mouse. I do have about 1.5 years of experience using a keyboard and mouse in Onshape, so as I get closer to that time and using the Steam controller more, I think they'll really start to even out, and you'll really start to see their strengths and weaknesses in different things. And as a final note, I just want to thank all you guys for watching.